Welcome once again to this lecture of industrial automation. So, as per our you can say tradition, we will going to start our lecture with a brief view of our syllabus for industrial automation. Look at this syllabus. We are at unit number 1, that is introduction to industrial automation, and we already have covered 1.1 to 1.3. We already have covered 1.1, 1.2 and 1.3, and now we are going to study the last part, that is point number unit number 1.4, that is different systems for industrial automation. And what are that systems? That systems are PLC, HMI, SCADA, DCS, drivers. So this unit number 1 is just an introductory part. In later units we are going to study PLC in detail, SCADA in detail, what is HMI, what is the DCS. But for this instant, just we are going to see the introductory part related to PLC, HMI, SCADA, DCS, drivers. So in front of you, you are having this um, in front of you, you are having this representative diagram of industrial automation. So this is the only for your reference. This is not actually any particular kind of industry. It is a representative diagram of automation, what actually automation flows looks like. So we are in day to day life, we are dealing with a lot of automated systems. We are going to ATM to withdraw a money, or uh, we are going to manufacture products with the help of CNC or VMC machines, or a lot of data that has been automated with the help of different types of automation systems. So there is a huge list of different types of automation systems, but they all are classified under certain similar characteristic systems. Therefore, by considering this view, we are going to differentiate different types of automation systems which can be classified according to their design or according to their way of. Actually, in our day to day life, we come across a lot of automated systems, and it's not mandatory that all automated systems work on the same principle. For example, whenever you dial a number, your call goes to mobile switching center, and mobile switching center route that call to a desired person. So routing of that call in very early days, that will be carried out with the help of operators, that is carried out manually. But in today's world, the routing of call takes place automatically. So telephone switchboards that also uses automatic working, but their principle is different. Also, just we have seen that whenever we go to the ATM to withdraw a money, that also works automatically, but their principle is different. Therefore, it's not mandatory that all the automated systems that work on the same principle. Therefore, we are just going to see what will be the possible types of systems for industrial automation. So mostly we are going to see artificial neural network, distributed control system, human machine interface, that is HMI, supervisory control and data acquisition, that is a SCADA, and programmable logic controllers, that is PLC. So first of all, we are going to see what is artificial neural networks. So what is a neural network? Neural network is nothing but in human body, our all the function, they are coordinated with the help of our neural network and brain. That's why neural networks are supposed to be one of the most intelligent automated system. Means human body is a best example of very superior automation. So in that regard, some systems are required immediate feedback to operate. For example, if something come in front of our eyes, then involuntary our we are going to close our eyelids. So that is carried out so fast, that is feedback mechanism there that our human body uses, that is tremendously fast. So in the same way, there are a lot of systems, a lot of automation systems which will require such a type of feedback, such a types of tremendous fast feedback. So mostly these types of systems are implemented in computer networks or data networks. So for example, if we open our Gmail or email system, then that email system, we are having separate portion that is related to the spam emails. So that spam email filtering is also takes place automatically, and for that a lot of algorithms, a lot of data patterns, they are continuously checking, computer system, they are continuously checking, and according to that it decides that whether the particular email is spam or whether the particular email is actually the authenticate email. Also system control in our car is also one type of artificial neural networks. Means that our car is having anti-lock braking system, our car is having what we say is cruise control system. So these systems are depends upon the feedback of physical matter. Means suppose there is a suppose that driver is going to apply a brake. So if he applies a brake, then what ABS does, that is ABS will prevent that car from skidding on the road. So that is a type of artificial neural network. In some systems such as radars, there is a lot of requirement of pattern recognition or actually where the object will go in future few seconds. So that is also type of artificial neural network. In okay also in today's world, in today's advanced mobile phones, we all are going to control our phone with our voice. Means if we have to search something, then just we tap voice search, and we speak, and according to our voice the Google may gives you a results. So that is also pattern recognition in speech, it is also some type of artificial neural network. So in this way there are a lot of artificial neural networks. We can classify a lot of automated systems into artificial neural networks. The next type of control system is a distributed control system. So as the name indicates, that control system is a distributed, means it is divided into a number of units, and each of every unit is working independently. These units are connected with each other with the help of communication networks. So generally in all the automation in manufacturing process in the industries where the manufacturing takes place, so there we implement distributed control systems. So one of the best example of distributed control system is traffic light controller. Means suppose in particular one huge big city, there are lot of traffic signals are there, and each traffic signal is controlling the traffic independently. So you can say this is as an example of distributed control system, and each traffic unit is also connected with the help of each other with communication network. Also these type of systems are implemented in oil refining, and also in central station for power generation. So these type of industries utilizes distributed control system, because in oil refineries or in power generation units, it's not possible to work that automation process at that particular unit, because that conditions may not be suitable for human being to operate that automated system. So in this way the control system is distributed according to the areas. um, this is also a type of control system. The next is a human machine interface. So what happen in this type of automation system is that human can be able to interact with a machine, and according to the command given by human, the automation system will works. The best example of human machine interface, that is also known as a HMI, is ATM. For example, if you go to the ATM and we press withdraw button, then it will, or we press make a deposit button, then according to our command that ATM machine will going to work. Therefore human machine interface, the best example of human machine interface is a ATM. The next type of automation system is a supervisory control and data acquisition. Actually, this system is mostly known as a SCADA, it's a short form. So, supervisory control and data acquisition is a very large term. In mostly all big industries, they are going to control the automation system with the help of supervisory control and data acquisition. Means with the help of sensors and with the help of actuators, all the automation process is carried out with human machine interface. So generally SCADA is very similar term, which is similar to a distributed control system. Sometimes it is very difficult to differentiate SCADA and distributed control system. But what is the main point which makes SCADA different from a distributed control system is that SCADA is just a supervisory. It do not in real time it do not control any machine. So SCADA is a supervisory control tool, and distributed control system, they are physically controlling that automation system. So this is the a mere difference between SCADA and distributed control system. Then a programmable logic controller. So the programmable logic controllers are also generally known as a PLC, which is a short form for programmable logic controllers. And they are a real time systems. They are real, in real time they are going to control the automation systems. Means a lot of sensor, lot of actuators, they are attached to a SCADA, to a PLC, and according to our design or according to our program, the PLC is going to control that peripheral devices. So that's why we call PLC as a real time system. So in many industries, a PLC is a part of your automation system, that is a field level part of automation system, because it is going to control all the sensors and all the actuators. The programmable logic controllers can be used to program a variety of day-to-day applications such as amusement park rides, and a lot of examples we can able to give here, which PLC may do. But just for this time, you remember that PLC is a real-time system. It is a logical unit. It takes a decision. It controls a peripheral devices. Now, just we have seen different types of automation systems according to their way of working, that are artificial neural networks, distributed control system, human machine interface, that is HMI, SCADA, that is supervisory control and data acquisition, and last, programmable logic controllers, that are commonly known as a PLCs. But another way to look at the automation system is how the products are being handled. So, if we consider this way of looking towards automation, then we are having two types of automation with us, that is a discrete automation and analog automation. So, in front of you, I'm going to represent a video which is from a YouTube site, that is a real parse. So it's very uh, it's very good. I can say it's very best YouTube site which will gives you idea regarding all the your questions related to automation. So I will suggest you to go through the real parse videos.
In this lesson, we're going to discuss discrete automation. Discrete automation doesn't necessarily mean that everything that happens within the process is done with only discrete signals. Discrete automation is more a term that is used for the process in which you can measure the finished component. Items that can be easily quantified could fit in the explanation of discrete automation. This manufactured item doesn't necessarily have to be done in one process. Let's first discuss an assembly process that would place a cap on top of a bottle. The procedure to attach that cap may be by compression, meaning that the lid is pressed onto the bottle, or the lid may be twisted or turned onto the bottle. This automation process would take that bottle into some sort of piece holder, while another piece holder would hold the cap. The automated process would attach that cap to the bottle in a single action, either by pressing the parts together, or one of the piece holders may spin in order to twist the cap onto the bottle. This automated process produced a product that can be physically counted. Of course, before the cap was attached, the bottle was probably filled with some sort of liquid, and the possible final step of this process may be to attach a label to the front of the bottle. It really doesn't matter how many steps it takes to complete the product. The end result is a countable item. However, just a small process, such as this one, isn't the only type of thing that would be considered discrete automation. Let's take a look at the process of making a cell phone. There are several parts that are used to create a cell phone. Those parts may include a plastic or metal case, an LCD screen, which can be a touch screen or just a display, possibly a keypad if it's not integrated as a touch screen, main circuit board, battery, etc. Now, each of these components may be made on a different production line, or in a different facility, or even in a different country. The process of creating each of these parts would be considered a discrete automation process. Each process is creating a quantifiable or countable part. When those parts are created in separate processes, they would then be shipped or moved to another production line that would then assemble those products into the whole, complete cell phone. The process to assemble the cell phone may take the cell phone
It's 1
case
o'clock.
and first install the screen. After that screen is installed, it may then be followed by the circuit board, the battery, the memory card, etc. When the cell phone is assembled, again, it is assembled using a discrete automation process. There are all of those components that were created by discrete automation processes, meaning they could count a component or part at the end of the process. Then you can take all of those countable parts and assemble them. The final product is a countable product, which makes it a discrete automation process. In discrete automation, the process is not necessarily continuous. The process of creating something via discrete automation could be started and stopped at any time. In other words, let's say that Plant A would create the cell phone case in a discrete automation process. Plant A needs to fulfill an order to produce 50,000 cases in various colors. The order is for 10,000 cases in stainless steel, 10,000 black, 10,000 white, 10,000 gold, and 10,000 rainbow tie-dye. The plant's process can create 1,000 cases an hour of a solid color and 500 an hour of a mixed or multicolor. The plant has only one shift, and that shift works 8-hour days and no weekends. So Monday, Plant A starts production on the stainless steel case. The shift was able to make 6,500 cases and planned to resume production the next day. On Tuesday, the plant resumes production of the stainless steel case for the final 1,500 count. If it takes an hour to change over the machine to produce a different color, the order for Plant A would take at least 8 working days to complete. If, however, Plant A had a 24-hour shift, this order would be complete in approximately 3 days. Basically, discrete automation production of components may be started and stopped no times or multiple times. The starting and stopping of an automation process can be done in either discrete or analog automation. However, starting and stopping a discrete process is as easy as stopping a machine after the last component is produced, and then starting it up again when you want to resume production. This is one of the easiest forms of process automation. In a future lesson, I will contrast the discrete and analog automation processes and demonstrate that with an analog process, the chore of starting and stopping is a much more difficult task. So, to sum it all up, discrete automation is the production of parts that are of a quantifiable nature. That may include cell phones, soda bottles, automobiles, airplanes, toys, etc. As you know, an automobile contains many parts. The parts required for an automobile are also quantifiable in nature. A car requires 2 or 4 doors, measurable. 1 hood and 1 trunk, measurable. 1 engine and 1 transmission, again measurable. Obviously, each of those required parts is not necessarily a single part in and of itself, but an assembly of other quantifiable parts. Once all of those parts are put together in a discrete automation process, you are left with a countable part, an automobile. This is discrete automation. Be sure to check back for more Real Parts videos. Analog automation is different in that while the final product may be countable, such as a carton of ice cream or package of cookies, the process to create these items is considered analog automation because of the way the manufacturing takes place. In analog automation, ingredients are tested and blended to create the final product. As with discrete automation, the manufacturing of a product doesn't necessarily have to be done in one process. Take ice cream, for example. Company A may combine heavy cream, half and half, egg yolks, sugar, and salt into a cooking vessel to make an ice cream base. This base may then be shipped to Company B that will combine it with flavors such as vanilla, strawberry, or chocolate. While the ingredients of the completed product were made separately, the final product was treated and blended to create ice cream. This is just one of many examples. Let's take a more easily explained procedure to demonstrate an analog automation process. I'll talk about a possible water treatment process to further explain this concept. The first thing that is needed for our water treatment plant is water. Let's say that our treatment plant has a few water sources, which are a reservoir, a lake, and some underground wells. Well, obviously, you don't want to drink water straight from a reservoir, and the thought of drinking a little lake water would frighten most snobbish fish and certainly most humans. These water sources need to be cleaned and disinfected, not only because we prefer it, but also because law typically mandates it. We're bringing water into the plant that is not so desirable, and the first thing we want to do is remove the big stuff. There may be leaves, sticks, trash, or even small fish or other animals in the water, and the first line of defense to remove these things may be some sort of straining system. Once the water exits the strainer system, it may enter a process of rapid mixing where it would be treated to balance the pH, if needed, as well as add specific chemicals that would make the particulates in the water stick together and form a substance of larger particulates called flock. The flock may then be pumped to a basin where everything is slowed a little, and the flock is allowed to grow even larger. After the flock has had time to develop, it may then be pumped to another basin where it is allowed to settle. This process would allow the large flock to settle to the bottom of the basin and be removed, while the top of the water would flow out of the basins to some sort of filtration system. The filtration system typically consists of gravel, sand, and a type of coal called anthracite. As the water travels through these levels of media, smaller particles and organisms are removed from the water. The water may then travel to a disinfection system. This system may be as elaborate as another type of filtration system, such as membrane, UV, reverse osmosis, ozone, or any other type. The disinfection process is determined widely by what the water quality is and the challenges for particle and organism removal. Are there bacterial or virus concerns? Does the water smell or taste particularly bad? Those are the sorts of issues that may require additional treatment. If the challenges are minimal, the disinfection may be as simple as adding chlorine to the water to ensure all remaining organisms are removed. Government typically mandates that there's some sort of residual chlorine remains prior to the water traveling to the distribution system. Once the water's been properly disinfected, it may travel to a holding reservoir that's used to store the finished product, or the water may then be pumped to travel through distribution lines that lead into the city that requires it. Other examples of analog automation are the continuous stream of gas and oil, pulp and paper, chemicals, and that sort of thing. While most of these products can be measured in some sort of way, a gallon of gas, a quart of oil, a drum of chemicals, again, this doesn't necessarily qualify them as discrete automation because of the way that the process is handled. The creation of a widget that ships to a company is much easier to quantify than a water treatment product. The definition of an analog automation process is more about what happens to produce the end result. Analog automation is about treating and blending things, while discrete automation is more about assembling different components to create a final product. As I iterated in the discussion about discrete automation, starting and stopping of an automation process can be done in either discrete or analog automation. However, the starting and stopping of a discrete process is as easy as stopping a machine. The starting and stopping of an analog automation process requires not only careful planning, but also advanced preparation. For instance, in order to stop a water treatment plant, the city must first determine where the water that the city needs will come from. If there aren't many possibilities of other city treatment plants to furnish the water, then the city may consider some short-term option, such as filling all storage reservoirs to capacity, and ensuring that the shutdown time is monitored and production is resumed in a relatively short time. Let's say that this is the option that the plant has chosen to take. They would first have to stop the influent plant flow. This may or may not be easy. If the plant has some motorized valves, they could command those valves to close and begin the shutdown process. If they did not have the motorized valves, the staff would have to travel to the location of the influent valve and manually close the valve. While this may sound relatively easy, some of these values are on pipes that may be 96 inches in diameter. That indeed would be a very large valve to manually crank until it was fully closed. With that chore out of the way, the staff will then have to stop the addition of all chemicals, as well as possibly drain the rapid mix basin. The reason for draining the basin would be that the flock would settle to the bottom of the basin and cause many problems for pumping to the next station, as well as equipment impact considerations. Of course, if they have to drain that basin, they may have to drain the downstream basins as well for the same reasons. The filters would need to be drained, as the stagnant water sitting in the filter would create an environment for breeding algae and other undesirables. In other words, all of the processes that it takes to treat water are affected by both short and long-term shutdowns. As you can imagine, the shutdown ramifications may be much greater with analog automation than they are with discrete.